So instead of doing a normal video where you have to look at my ugly face, I decided to go ahead and just talk at a screen and you can just look at the images. They're more useful than my face in this case. So, physics fundamentals. It's not necessarily how the process of physics actually works. It's more of what you need as a programmer to make sure you accommodate all the weirdnesses that come with it and how vector math works in a game environment, because there's all sorts of errors creep in and weirdnesses that come from coordinate systems that don't make any sense. So this video covers those fundamentals that we require for all the later videos on physics that I'll make. So let's start with the simplest component in physics. In the game world, it's going to be a vector. It might be a 2D vector or a 3D, but in this case, we're going to use a 2D vector. We can make one that points up, and it has no real location, so we can move it around the screen, and it's always exactly the same vector. It's always pointing in the same direction, it has the same effective length, and it doesn't really matter where it's at. We need to put some kind of point of reference. So that's going to be the standard point that you might have learned in geometry. And once we have that, then it anchors it. And we can rotate it around that point, and it probably still looks like it's pointing up. But without having some kind of coordinate system, up really actually means nothing. We have a monitor, so we kind of have a reference to think that it is pointing up. But if I point it this direction or that direction, it's still pointing up based off of how we have the screen oriented. And the other problem is now we don't know what a length means. So what does 1 unit mean? To solve this problem, we need some kind of coordinate system so we can kind of get a point of reference for everything we work with. So this is probably the most common and well-known grid system. We have X and Y, where up is a positive value for Y, and to the right you have positive values for X. And this is pretty much common in most games as well. So if you jump, you move up on the Y, and if you move forward, it's generally going to be moving positive value on the X. But when you're dealing with computer monitors, everything works on the Y being opposite. We have positive values going down from the top of the screen, but you still have right equaling positive values for X. Some game engines have easy methods to flip back and forth, some do it automatically for you, and some might even have positive values being down for inside the game world. And that gets really confusing. When dealing with a vector inside of a grid coordinate, generally the start position anchors at the 0, 0 position on the XY coordinate, and then it goes off in some random direction determined by its values for each X and Y. So in this case, we have the Y value being a little shorter than the X value, and you can form little triangles using right triangles off of the X and the Y coordinate system. And the overall length is a simple math formula you've probably learned, and I don't need to repeat it here probably. But that's going to be, in the game world, often referred to as magnitude instead of or length, depending on the engine you're working with. The combination of X and Y coordinates is generally considered the direction of the vector. So because we have right triangles, we get the benefit of being able to use all the basic cosine, tangent, and sine laws in order to determine what particular angles are or the length of particular sides if we only have an angle. And we also get to use a squared plus b squared equals c squared, which is the overall length of the vector. And from that, we can do other calculations that are useful. Just remember when you're working with the angles that games generally calculate based off of radians, not degrees. There's usually some kind of method for switching back and forth because we generally understand degrees easier, but radians is the most common that I've seen. So this normalized vector, a lot of vector math I'll go into in a later video will need some kind of standardized length vector in order to do calculations, and that's called a normal or a normalized vector. And you can convert that using that Pythagorean theorem in order to calculate a new vector with the length of 1, and then determine what the x and y values are going to be based off of the math on the screen. So also with vectors, we get the nice bonus that we can add them together because it's just general addition and subtraction. And we can add them in or subtract them in any order we like. When we start dealing with multiplication and division, order starts to matter just like basic math, so use the standard rules. But the nice thing is when we add them together, we get a whole new vector, and that can be a series of forces that we apply together in one frame, and we get the overall direction of movement for one moment in time by just adding the vectors together. Nice and easy, lots of math, but it's not too bad. We also have a result vector that has a set x and y value, and we can calculate that with some simple math. If I take my ugly arrow image and give it a center point, I can add a vector to that center point and make it look like it's traveling through space. And if I have a set amount of time per frame, then I can do a quick calculation to simulate some kind of speed. As the vector moves from one place to another, it eventually looks like the arrow hits the ground and then it stops. But because I'm using a vector to move an object from one place to another, it's actually teleporting from one place to another. So it looks like a flip book and it feels like movement, but honestly it's just separate images teleporting from one place to another. Result is that there's no object that can collide between the two center points. If I have a wall, the arrow will go through the wall if the vector doesn't end inside of the wall or some kind of contact with it. It just teleports through it and continues flying until it hits the ground at the other end. And this is a really difficult problem to solve. The simple solution is usually reduce the frames down to a smaller length, but not all problems can be fixed like that. And we'll get to that at the end of the video of explaining why that doesn't work. But the big point is that objects teleport, they don't fly continuously from one place to another. So it's a little bit unlike our own normal experience, and we kind of assume things slide from one place to another, but in a game it just doesn't work that way. So one of the other weird issues we have because of vectors is that the physics result as we move the arrow from one end to the other is that it's going to land in the wrong place. Normal physics calculations can accommodate for continuous movement and curve, but we're working with a sample, and the individual samples are straight lines from one place to another. And the result is that as things curve and move around more and more over a longer period of time, error kind of creeps in. The result is that in a game, the physics result is wrong. The normal solution for this is to reduce the physics down to a shorter amount of time per sample, but you only can do that so much. And the result is something a little more accurate. But honestly, it's a game, so people aren't going to be doing math calculations to check it. As long as it looks realistic, it's perfectly fine. Because we can replace an XY coordinate system with a vector, we can have a vector that points anywhere. So in the world coordinates, the movement might be along a straight path, but to the actual individual inside of this ugly plane, they can keep themselves on target by just rotating to the right-hand side a little bit as they fly along. And they can keep the target dead center so it looks like they're not really moving at all. And the benefit is that it's actually a lot simpler to program this. We can just have a joystick, okay, we moved it a little bit to the left, a little bit up or down, and we just send that off to the game engine in order to do some basic calculations for us and convert those small movements into radians that change inside of the world view. And we can switch back and forth between them, basically at will, and we'll have to do that quite a bit. The nice thing is that in the local world, the plane, my guns always aim forward. I always look forward, or I can look a little bit to the side or one or the other in a 3D game. But for the most part, we just orient ourselves to the front of the aircraft And we don't even care where that front of the aircraft is actually looking the side of the main world at all. So with 2D, we had an issue where the Y could be positive going vertically or positive going down in different situations. And it's confusing, but it's easy to work with. When we're dealing with 3D, now we have the complication of the Z-plane. So is positive coming in and out of the screen? Is it going backwards? Is it coming forward? And now you have to worry about which way is which. It gets pretty confusing, and every engine seems to be a little bit different. It all comes down to this issue of, is it left-handed or right-handed? And there's lots of videos to explain that. I'm not going to go into it in this one. But it starts getting really confusing really quick, so make sure to check your game engine's documentation of which one they're going to use. To make life even more confusing, some games will have a Z-plane being up and down, and the Y-plane being in and out. And then it comes down to which way is going to be positive value. And it gets really confusing. But what makes it even more confusing is when you start panning around in a 3D environment, then you start losing perspective of what even the X direction is. Normally, games have X's off to the right in order to be positive. But as you start rotating and gaining perspective on the world, that X plane might start pointing to the back. Then the Y plane will start pointing to the right. And then the Z plane will have some other angle going with it. And it starts rotating through and becomes very difficult to understand sometimes. And things start getting very, very weird. As an example of how weird things can get when you start working with 3D. With this question is, how many straight lines do you see? Do you see one? Do you see two? Do you see none? Or any line straight? If I give it some kind of perspective, it starts looking like probably the orange line is straight now because it fits on the grid coordinate system quite well. And now the white line seems to be bent, because that's the way the coordinates work out. But if I start giving perspective on the white line, now it looks like the orange line is pushing to the back and the gray line is actually straight along the X plane, where before it looked like it was laying along the Z plane. So it starts getting really confusing. So now how many straight lines are there? The answer is there's actually no straight lines whatsoever, because it's just a 2D image. And the gray line in this case is straight on my screen, but if your screen is curved, then it's neither of them are straight. And that's where things start getting really weird. The benefit is that humans live in a 3D world, but we literally see 2D, so we're really good at processing how 2D turns into a 3D in our brain. And because we get really good at it, we can use flat monitors, we can have 2D images, and we can pretend in our mind that we're inside of a 3D environment. Earlier in the video, I mentioned that we can solve a lot of the physics problems by just shortening the amount of time we take per frame. If we increase the frame rate, then we get less time to actually process the actual information. And it becomes a problem because eventually it becomes so small we can't actually process all the information we need per frame. So it's very limited, even if we have unlimited number of cores, because time just doesn't work as well as we want it to. So the other issue we have is that floating point values aren't infinitely long. Normal one is 32-bit floats, and that gives us 24 bits of precision. What that basically means is you get about 4 digits past the decimal to work with. But weird things do happen, and when you start doing math with limited amount of precision, you get weird things like A plus B equals A, even though B should be added to it. Or if you have a situation where you have a small vector that's perfectly normal to have a 0.01 movement in a frame or over a second, and then you divide it by 500 frames per second, which gives you a reasonable value of 0.00002. But if you add that to 1.1, you still get 1.1, which is really odd. and it will drive you nuts when you're making computer games. So you have to worry about how many operations you do per second because the math breaks. Or if you're dealing with taking a vector and applying it to an image, and then you move that image based off of the vector, images are based off of integers, not floating point values. You can easily have a situation where you add 1 to 0.1 and you still get 1, so your object never moves ever. So you have to do things like store the position of the object in a vector and keep adding to the vector, not the point that is the center. Every frame, you have to waste a few cycles, convert your floats back into ints, and you end up not having rounding error. After 10 frames in this case, you would actually see 1 pixel worth of movement. And things get really weird if you don't handle that properly. So with that, this becomes a lot of issues where floating points just aren't good enough. So the temptation might be to use a 64-bit floating point value or a double, which gives you far more bits of precision. The problem is that games always use floats because floats are faster through the CPU than a 64-bit integer or 64-bit anything, honestly. So if you have that situation, you might be tempted to use doubles, but now your math doesn't work at the same speed, so everything takes longer. Or fix that problem, maybe you start storing things as a double, but process things as a float in order to process faster, but now you're wasting time because you're converting from a double to a float and back and forth, back and forth. Then the temptation might be, well, fine, throw the whole package out because no engine's going to support finer movement like I want because I want to have 500 or 1,000 frames per second. Well, then now you have to design your own engine, and that's going to take 3 to 5 years of work just to cover up that one little small error. And now you're death by math because math errors creep in with all the engine problems that someone else has hopefully solved already. So that's kind of the problem with a lot of this math, and errors do creep in because we're working with digital, we're not working with analog or continuous movement. So we have the same issue with floats as you have with the vectors themselves being a sample of the actual truth that you're looking for. So that's game physics and all the weirdnesses that come with it. Hopefully it's helpful for you. If it was, like and subscribe, and leave some comments below.